Yeah, I use that for FE.
It's crazy.
So
So did you made it through the environmental exam?
I mean, the exam is closed, yes.
I didn't
Made it.
I put some stuff down.
I thought it was easy and it scares me. I just put my name on it and turned it in.
Everybody's settled down.
I did the true or false.
You did the true or false?
I don't know if I did those right.
I did do true or false.
Okay.
Okay.
All right, everybody. So there's not a whole lot to say in terms of announcements because all the outstanding homework was graded since the last homework. I haven't yet uploaded the attendance grades from Monday. I'll probably just lump them all and do that at the end of the week. The survey was mostly in favor of moving the exam on Wednesday. There were still some folks who wanted to keep it where it is, and I will let me get back to you on it because there's a possibility I might just offer the exam on both days. I haven't really decided yet, but it's far enough into the future that we don't really need to worry about it right now. I just wanted to get sort of a rough idea of where everybody stood on it. Homework 5.1 was due. Did everybody have an okay time with the Excel homework? Hopefully you got a curve that looked like that. What? That's a very technical term. And then homework 5.2 is assigned today. This is going to be the first sort of like real assignment related to columns. The reason for 5.1 is, as you saw, the equations are a little unique, and I want that part to be comfortable. I don't want the use of those equations or the manipulation of those equations to be complicated. So with that, let's go ahead and get into actual column analysis. But before we do, there's one thing we kind of need to discuss to make sure that conceptually everybody understands, and that's the idea of strong axis behavior versus weak axis behavior. Okay? So it would help if I plugged the remote in. I always forget to do that. All right, so first off, let's just make sure that we're all sort of familiar with the expression for FCR because we're going to use it today. I don't think I emphasized this in class last time, but for the inelastic column range, that Fy, Fe, that fraction, that's an exponent. It's not 0.658 times Fy over Fe. It's 0.658 raised to the Fy over Fe. And so again, it just fits the test data quite well. So if you're going to compute FCR, the first thing you have to do is you have to compute Fe. And so you need, in order to compute Fe, you need a modulus of elasticity, but you need a slenderness. Okay, and today what we're going to be focusing on is that slenderness, actually determining it. You got to sort of put your noggin on it, make sure you understand where that slenderness is coming from. But once you get it, the calculations are pretty methodical. You compute Fe, and then you compute FCR by comparing the slenderness to 4.71 square root of E over Fy. So the only thing left to determine is how do we get that slenderness. Now, the slenderness that we use for a column is KL over R, not L over R, and the K is the effective length factor that we use to map our solution to that which we derive for a pen-pen column. So if we have a pen-pen column, then our K value is 1. But if our boundary conditions are different than a pen-pen column, then we must adjust the length so that the buckled shape, the buckled length matches that of a pen-pen column. And remember to make sure that you're using the recommended values, not the theoretical one. Because, you know, for example, if we look at case A assumes a fixed boundary condition, and there's no such thing as a boundary condition that's perfectly fixed or perfectly pinned. Those are mathematical abstractions. They don't exist in the real world. Even if you connect it, you know, with the most beefy connection that you can think of, there's still going to be a little bit of rotation. That's just physics, so you can't get around that. All right. So now what we need to do is we need to talk about L over R and determining the controlling L over R. And in order to do that, we need to understand strong axis versus weak axis behavior. Okay? So I want to talk about W shapes and sort of explain what I'm talking about. All right? If you go to table 1.1, what you find are the properties for W shapes. Okay? Now table 1.1, it crosses two different pages. So if you just open it up and look at table 1.1, let's sort of discuss that anatomy a little bit. The stuff that's on the left side of the table, the stuff that's on the left page, bless you, are all dimensions. Things like, what is the depth? What is the flange width? What is the flange thickness? Like stuff that you could basically break out a tape measure and actually measure out in the fab shop or out in the field. Okay? But everything that's on the right are computed section properties. Okay? And you see things like compact section criteria, and then you see a column that says axis XX, axis YY, you see torsional properties, etc. Those are computed properties, okay? Most of them are flexural properties, some of them are torsional properties. So the torsional properties relate to understanding how much an I shape or a W section will twist under a torsional load, whereas the axis XX and axis YY stuff are all flexural properties. How the section will respond if it's being bent, okay? Which makes sense for columns because when a column buckles, it buckles in a flexural mode. So obviously it's going to be function of things like the moment of inertia and what have you. Now in our derivation, what we did is instead of using the moment of inertia, we used the radius of gyration. And the radius of gyration is just a normalized version of the moment of inertia. So if you take the moment of inertia of any shape, divide it by the area, take the square root, you get the radius of gyration. So it's basically the same thing. Now one of the things that you will notice, if you just open up and look at any W shape in the manual, you will find that for any W shape, Rx is always bigger than Ry. For every one of them, okay? And that is by design, okay? One of the reasons that we configure an I-beam the way that we do is we say, okay, I want to configure a steel shape such that I get as much steel material away from the centroid as possible, all right? Remember that whole parallel axis theorem, the moment of inertia is the sum of I plus AB squared? The further away we can get material away from the centroid, the bigger the moment of inertia is. And the bigger the moment of inertia is, the stronger the section is under bending, okay? So that's why I shapes are the way they are. We have two plates and we stick them as far away from the centroid as possible and a plate in the middle to connect them. So by that stretch, by that logic, there's going to be one moment of inertia that's always bigger than the other, and likewise, one radius of gyration that's always bigger than the other, because that's the way we configure them. So if you look at the x-axis and the y-axis, the Rx is always bigger than Ry, so we have a terminology for that. We call the x-axis the strong axis, okay? We call the y-axis the weak axis. So if you ever hear me say strong axis versus weak axis, this is what I'm talking about, okay? Now this isn't always the case for every shape. So like for example, if you're looking at WTs, there might be WTs where Ry is bigger than Rx, but because we're not looking at a shape that's like an I cross-section, the shape is different. The other thing that's worth mentioning is that if you're looking at shapes that do not exhibit symmetry, like an angle, we have an RZ. That's basically taking the moments of inertia and plugging them into a Mohr circle and figuring out the worst case scenario. Okay, now let me explain the effect of bracing and boundary conditions, okay? And I want everybody to just sort of follow along with me, and let's take a look at what's going on. So I want to look at a W-shaped column that's pinned on both ends, okay? Let's just use some numbers, okay? So we're going to say that the column is 20 feet long on both ends, and what I have here is a bracing diagram for each axis. It'll be a lot easier to understand how this comes into effect in the real world here in a bit, but just for the sake of discussion, just bear with me, okay? Now, I have a column, and let's say we're talking about the same column. This is what it looks like on the x-axis, this is what it looks like on the y-axis, okay? Now, let's say the column's 20 feet long, and for simplicity, let's say that this is Rx, and this is RY. Doesn't really matter what the shape is, I just pick these values out of a hat. Okay? They're pretty representative of what you find in the manual anyways. Now, the column is pinned across the board, so if I open up the commentary in the steel construction manual, I find that K is 1. Okay? So a question for you is, how is the column going to buckle? Okay? Well, let's take a look at the slenderness values. All right? So, let's do this together. Let's actually do this together. All right? So, here's what I'm going to do. I'm going to need some help with the Casio FX115 ES Plus or similar scientific calculator. Okay? So, let's move this over here. Let's do KX LX over RX. Let's compute this. Let's see what we get. So, K is 1. Okay? L is 20 feet. RX is 6.2 inches. And then this is in feet, so I need to convert that to that. What do we get for this?
38.71.
38.71. Do I have a second on that?
Yeah.
Okay. What are the units for that expression? What are the units for this? There are none. Slenderness is a unitless quantity. Okay. So just make sure that everybody remembers that. There are no units for slenderness. Now let's do KY LY over RY. So 1.0, 20 feet, 12 inches per foot. And then now 4.1 inches. We'll do IM. So what do we get for this?
58.54.
58.54. About a second. Okay, all right. Now, so let's think about this. What am I computing? I'm computing KL over R. KL over R, these are slenderness values, right? The higher that number is, the more slender the column is, okay? Now, what do you think that does to capacity? If I start increasing slenderness, what does that do to column capacity? It decreases it, right? Now, you found that out in the last homework assignment because you had your graph, you had KL over R over here, you had FCR over here, and then using my sound effect, it does that, right? But what that basically is saying is that as the slenderness goes up, the capacity goes down. So if you're a structural engineer and you're trying to determine how strong that column is, what value are you going to use to predict the capacity? This one, right? And that's exactly right. I propose that if you load this column in compression, the column that we see right here, it will buckle about the weak axis. Does that make sense? Okay. Now, the question then that I want to ask is, could it ever buckle about the strong axis? If Rx is always bigger than Ry, could a column ever buckle about the strong axis? Yes. Okay. It is very possible that a column could buckle about the strong axis because what matters is not what the deal is between Rx and Ry. What really matters is which segment, which unbraced segment yields the largest slenderness, the largest KL over R. Let's take a look at this example. So I have a column here, and I have an isometric view that I've drawn up to kind of explain what's going on. I have a column that is 35 feet long, okay? And what I've got is I've got braces that are framing into the column. Those braces are framing into the column, preventing the column from buckling about the weak axis at various points. Now, a real-world example of where you would see a column like this is like a hotel. How many of you have ever been in like a big hotel in a big city, and you go in and the lobby is like 3-4 stories tall, and they've got The lobby's 3-4 stories tall, and then you can look and you can even see rooms in the lobby that extend out. Okay, so you've got columns that extend maybe 2-3 stories out for the big lobby or the big atrium, but then adjacent to that are rooms framing in for the adjacent stories. Okay, I propose that for this column we have a different bracing configuration than we would for the column I just showed. So for example, that column is actually going to look something like this. The x-axis is completely unbraced for a length of 35 feet, but the y-axis has intermediate bracing, and we have different bracing configurations. So let me make my point here. Let's go back to my question. Could the strong axis ever govern? I say yes, because let's go back to our original example. What happens in this original example if I go to the y-axis and I put a brace right in the middle of the column? Well, if that's the case, then I have a KL over R in the x-axis that didn't change, so it's still 38.71, but what about the y-axis? Well, the y-axis, I now have 2 segments, and for the y-axis, I'm going to have KY LY over RY. What's going to happen there is it's going to be the same K value, same radius of gyration, but instead of it being 20 feet, it's only going to be 10 feet. And so what do we get if we do this? We're going to get half that slenderness. What's half that slenderness? Is that 29.27?
Yep.
So the idea is this. If I have a 20-foot column that's just freestanding by itself, I propose it's going to buckle about the weak axis. But if I stick a brace right in the middle of that column, preventing buckling about the weak axis right in the middle, that maybe that column will buckle about the strong axis, because the slenderness about the strong axis is larger. Does that make sense? Anybody have any questions on that? That's a concept you really got to wrap your head around to make sure that you're clear about what's going on. Sound good? Okay, if you understand that, now we can get into column analysis. Now, there are 2 ways that we are going to analyze columns in this class. And the reason is that the second method is going to be absolutely and totally necessary for designing columns. Okay? Now what we're going to do is we're going to start off with the first method, and the first method is just a straight calculator. Just a straight calculating it using the equations from section E3. What are the equations from section E3? What you all plotted in your homework last night. The second is to use one of the design aids in the manual. And the reason we need to review that is because you can't select columns without design aids. You see, this is the thing where column design and beam design starts to get a little different. To be frank, we really didn't need much in the way of design aids to design tension members or bolted connections or welded connections, because the math was really easy. It was really straightforward. Like capacity was just phi Fy Ag. Just solve for the area. It's pretty simple. Columns, not so simple. Here's the equations for columns. They're a little weird, okay? So as such, coming up with some nifty little plug and chug method for computing the, or for determining the capacity of a column or designing a column doesn't quite work out. You need some degree of design aids in order to design a column. You all paid X number of dollars for your manual. What you were really buying were those design aids. And so you're going to see that here in a little bit. So how do you analyze a column? Well, you determine the largest KL over R for that column, and then you plug into your expressions. And that's what we're going to do today. How we handle method 2 and how that design aid works, we're going to get to that here in a bit. Let's actually go through a step-by-step process of analyzing a column using method 1. Okay? So let me pull this up and let's take a look at it. Okay. So just so everybody's aware, the x-axis, we are completely unbraced for the whole 35 feet. For the y-axis, we've got some intermediate bracing. I'll give everybody some time to sort of copy this down, but I do want to make a couple of notes. One of the biggest notes I want to make is about Fy. Unless otherwise stated, from here on out for the rest of the semester, Fy is 50 KSI. 50 KSI is the most common yield stress for W shapes. And from here on out, we're focused on W shapes because columns and beams in commercial structures, that's primarily what you use. I mean, think about what they built, the 4th Avenue business building, or the 4th Avenue Innovation District. Those are all W shapes, every one. Now this column is going to be a 14 by 90, A992 steel. We are going to compute the capacity of this column, and I say using method 1. Method 1 and method 2 are just my names for it. Really, that's just using the equations. So I'll give everybody a sec to copy this down. We'll get into it. Let me move this over. Hold on 1 second. Ooh, that's loud. Could somebody help me out? We're dealing with a 14 by 90. What is the gross area and then the moments of inertia about the X and Y axis? Because we'll need those properties in order to analyze the section. Take a second to look that up. Remember, it's 14 by 90. $26.5 for the area. What about RX? 6.14. And what about RY? Oh, typo there. What about RY?
3.70.
3.70? Okay. Okay. All right. Now, before we move on from this image, okay, so what I have here is the strong axis bracing, and then I have the weak axis bracing, okay? So what I'm going to do is I'm going to number these. So what we'll do is we'll say this is segment 1, this is segment 2, this is segment 3. So I'm going to number each of these segments, and you'll see how I reference that here in a bit. But for each of these segments, we're going to need a K value, okay? So let's start off with the x-axis, okay? So this is where we're going to have to go back into the commentary, okay? K values are on page 16.1-570. So if you haven't tabbed that, I would. Okay. Let's start off with the x-axis, okay? So we have a column that is fixed on the bottom, but it is pinned on the top. What is the K value for that segment on the x-axis? Is that environmental testing?
2.1.
Ooh, hold on.
I don't know if I'm looking at the right one though.
2.1, that's one that's fixed on the bottom and free on the top. We need one that's fixed and pinned. Now, all right, you said 0.7. Now that's the right case, but that's the wrong value. 0.8.
Oh.
We always use the recommended values, not the theoretical ones. So we tend to bump up the theoretical ones a little bit to account for the fact that those fixed connections aren't fully fixed. So this one is going to be a K value of 0.8. Okay. Now what about the y-axis? Okay. So segment 1 and segment 2 are both the same boundary conditions, pin, pin, and pin, pin. So what's the deal with segment 2? What's the K value there? 1. Okay, and then segment 3, the K value is going to be 0.8. There we go. All right. So this is a K value of 1. K1, K 0.80. All right, does everybody see that? Okay, one thing I would make sure that you recognize is if you look at, for example, because this is going to affect your homework, case C. So case C, the bottom is fixed, but the top, what it's saying is that it's prevented from rotation but free to translate. And if you could look, you can see on case C, there's a box on the top. There isn't a box on the bottom. And I'm going to use that boundary condition on a homework assignment. So just make sure you recognize those symbols. The symbols I use match those here. So, okay. All right. So now what we're going to do is we're going to go into analysis, and we're going to determine first the worst KL over R. And by worst, I mean the highest. Okay. So what I'm going to do is I'm going to have myself, I like doing this in a table, okay? So what we'll do is we'll say case here, okay? And so I'll show you how I'm going to do this. I'm going to say that this is case X, Y1, Y2, Y3. Because there's 3 on the Y-axis and only 1 on the X, so just keep it simple, okay? So the first thing I will do is I will list the K values, okay? And what we looked up was 0.8, 1, 1, and 0.8. And if you want, what you could do is you could say this. Do y'all know what I'm doing there? Those are the cases in the table. Like this is case B, case D, case D, case B. All right? Now what I'm going to do is I'm going to write the length. Okay? But what am I ultimately going to have to do to that length? I'm going to have to convert it to inches. So for the x-axis, how long is that unbraced length for the x-axis? It was 35 feet. So what's 35 times 12? 420 inches, okay? And then for the y-axis, it's what, 10, 15, 10? Did I get that right? So 10, 15, 10 is 120, 180. I think I can do that one in my head. So 10, 15, 10. So now I've got the lengths. What about the R's? What about the radii of gyration? Well, for the R, we know that for the x-axis, it's what?
6.14.
There you go. But for all 3 of the y-axes, it is
3.7.
So now just KL over R. Okay? Now, I kind of like to use 3 decimal places, and the only reason I'm doing that is just so that in the class we're all getting the same answer. You can probably go with 2, that's probably fine. I wouldn't go with less than that, but that's just me. All right, so what are we getting for the first row? 54.7, I think it's like what, 723?
Yeah.
Okay. What about the second one? What again? What's that?
444.
444? Was something squared? Because I got 32.432. There might have been another 12 there. What about, did anybody else get 32?
Yeah.
All right. What about the next? I think you might have another 12 there. The next one. Tell you what, I can do that one. I'm getting 48.65. And then the last one, I got 25.945. That match what everybody else got? So which value do I use for the purposes of computing the capacity?
First one.
The first one, right? So that one's this one right here, okay? So what that tells me is the strong axis governs and KL over R is 54.723, okay? That strong axis governing, I just want you to keep that in the back of your head. That's kind of important. Now, once you get KL over R, the next thing to do is compute the capacity. Now, a lot of this I think you could probably walk through with me because of the homework last night. So, the next thing we need to compute is the elastic buckling stress. Which is pi squared E divided by the slenderness squared. So that is pi squared. What's the Young's modulus for steel? 29,000 KSI. I want that number burned into the back of your head by the time you graduate from Marshall University. And then the slenderness is 54.723 squared. Make sure you square that bottom number, okay? So let me know what you get for that. And I do want everybody to kind of go through this math because this is the type of thing you're going to have to do on an exam, and I want to make sure this is comfortable. I don't want, like, you got to be able to do this. So
95.6.
okay, I'm getting, yeah, it should be something like 95 point like 578.
Yep.
Everybody getting that? Now, I want to be clear, that does not mean that the column can hold up 95.578 KSI. That wouldn't even make any sense because the column has a yield stress of 50, right? I know it can't hold that up. We're not saying this is the capacity. All we're saying is that this is a useful parameter in computing the capacity. Now, in order to determine the critical buckling stress, first, we need to do a comparison. So KL over R is 54.723. Now we need to compute that limit, that 4.71 square root of E over Fy. Because basically what we're saying is If KL over R is bigger than that, then we're in elastic buckling. If it's smaller than that, we're in inelastic buckling. So 4.71 times the square root of 29,000 KSI over 50 KSI. And so what is that?
I got 113.432.
Do I have a second? Okay. So what I can say is if I'm comparing KL over R and 4.71 square root of E over Fy, that's certainly bigger, right? And so if KL over R is less than that, inelastic buckling governs, right? And if inelastic buckling governs, therefore, our critical buckling stress is that exponent equation that y'all used in the homework, not the 0.877 FE. So it's 0.658 raised to the Fy over Fe, and all of that times Fy. So, let's see what we're getting for this. Again, this is one of those expressions I want you to make sure that you're all comfortable with the math and that we're getting the right answer. Because again, these are equations, these are the kind of things that you're going to be doing over and over and over again. So the more comfort you get with it now, the better. $40.168. Do I have a second on that?
Yep.
Okay. Now that makes more sense from a capacity standpoint because the yield strength is 50 KSI and the column can hold up about 40 because it's reduced because of the presence of buckling. So now, if I want to compute the factored resistance, phi Pn, it's just phi F critical times the area. So again, it's the final equation is set up a lot like a tension member. It's a phi value times an area times some stress. It's just to get to that stress, there's a lot of hullabaloo to go through. So we have 0.9 times F critical, which is 40.168. And then what was the gross area again?
26.5.
26.5. And so what do we get for that?
$958.
958.0 kips. Do I have a second?
Yeah.
Boom. There's the answer. We're going to come back to this page here in a bit. We may not finish this last part today, but we'll see. All right. Any questions? Okay. Now, before we go on to the next example, I want to write a couple things on the board for reference, and there's really only two things I want to write, just so I have them in the back of my head. So, strong axis governance. Okay, so I just wrote down the capacity and I just wanted to note that the strong axis governed. And we figured that out up here by looking at the slenderness, okay? When we use the design aid in the manual, we're gonna figure that out a different way, but we're gonna get the same answer, okay? Now, the only other comment I wanna make about the problem from a homework and exam perspective is this part right here. Does anybody see how we might have wasted a little bit of time on this problem when we looked at the slenderness? Does anybody kind of see that? We computed all the KL over R's. Could we have eliminated a couple of them by just looking at the bracing conditions?
Yeah, I mean, the length is gonna govern.
The what?
The length, the longest length is always gonna be the one that
Well,
goes.
it's not just the longest L, it's the longest KL.
Well, okay.
Okay, and so if we look at the y-axis and we look at the three segments, the middle segment not only has the largest length, but it has the largest K value as well. So we didn't even need to do any math, any of that tabular calculation for segments 1 and 3, because it was never going to govern to begin with, right? Okay, and it might sound silly, but I kind of think we actually needed to do the calculation so that you see that we didn't need to do them, right? So if you're on an exam, like if you want to be systematic about it, yeah, you can check all of them, but it's not that necessary. Really? You know? You can just look at it and see it's not going to govern. Does that make sense? Okay. All right. Okay. Any questions about computing the capacity according to using the equations, according to method 1? Okay, good stuff. All right, now I want to talk about method 2. And method 2 is using table 4-1. I want everybody to turn to table 4-1 right now. This is a tabbable guide in your manual. This is an incredibly important design aid. In fact, it is so important that if you open up the reference manual in the FE exam, they have placed a snippet of this table in the FE reference manual, because you literally cannot design columns without it. It's that important, okay? Now, the point is that a lot of the computations that we've done just now can be kind of labor intensive. I think, as you realize, if you're trying to do every column, table 4-1 makes our life a little easier. Now, one of the things that I am going to mention right off the bat is that if you notice, we are in table 4-1A, okay? Make sure that when you're using this table, that you are using table 4-1A for 50 KSI. Table 4-1B, I believe, is for 65 KSI. So it's really easy to just be flipping through pages in the manual and be on the wrong table. That will drive you nuts on an exam problem if you are getting column selections that make no sense, you know, probably because you're in the wrong table. So just make sure that's clear. This tool is incredibly vital, okay? Now, there's a couple of things that I kind of want to point out in the table before I show you how to use it, okay? The first thing I want to show you is, so if you look at the way the table is structured, there is a column for every shape. Like here's the W12 by 96s, here's the W12 by 87s, here's the W12 by 79s, here's the W12 by 72s, etc. And then what each entry in that column is telling you is what is the capacity as a function of its length. So if the column is 6 foot long and it's a W12 by 87, it can hold up 1,110 kips. If it's a W12 by 65 and it's 11 foot long, it can hold up 747 kips. And I'm being a little fast and loose when I say long, and you'll see what I mean here in a second. Remember, we're using the blue numbers, not the green ones, or the unshaded numbers. Okay? Now, the other thing I want to look at before we start explaining how this table works is what's on the very bottom. Y'all see what's on the bottom? If you look at the column or of the table, there are a lot of section properties for each of the columns. The gross areas, the moments of inertia. But anybody see one that looks a little weird? Like, why is there a ratio? Y'all see the ratio where it says Rx over Ry? And it'll probably say like Rx over Ry equals like 1.6 or 2.1 or something like that. Y'all see that? Why is that listed? It's kind of weird. Well, the reason why that's listed is because of what is going on in this column, this text right here. What does this column say? It says capacity with respect to the least radius of gyration, Ry, okay? Now, so what this table is doing is it's basically saying we're going to assume that the weak axis governs and that we're going to compute capacity every foot, assuming that the slenderness is computed for Ry. So KL over R for 6 feet, KL over R for 7 feet, KL over R for 8 feet, KL over R for 9 feet. But they're assuming that the weak axis governs. What's the problem with that? We just did a problem 5 minutes ago where the strong axis governs. So how do we use this table when we are looking at sections where the strong axis governs? Here's how. Okay, so what we do is we set those two values equal to one another, and we solve for an effective KL about the y-axis. So basically what we're doing is we're saying Kx Lx over Rx equals Ky Ly over Ry. And if we want to check the strong axis, what we'll do is we'll say, let's multiply both sides by Ry, and so we get Kx Lx times Ry over Rx equals this. Or if you multiply by this fraction, what it means is you're dividing by its reciprocal. And we call that sort of a KL effective. So what we do is if we're checking a column, we can go into this table with either the weak axis length or an effective strong axis length, where we take the strong axis length and we adjust it by dividing by the ratio of Rx over Ry. Once we do that, we got to break out this. Ooh, y'all remember that? Remember that? That whole linear interpolation thing? Like, we engineers, we don't like linear interpolation. And I go, well, that's kind of engineering. This is horseshoes and hand grenades. The whole close enough type thing. Okay, so the way that we use column or table 4.1 is we say, okay, what we're going to do is we're going to look at a column and we're going to determine the largest KLX and the largest KLY. And then what we're going to do is we're going to go into that column, into that table with either KLY or KL effective, whichever is largest. And so what we're going to do is we're going to use those quantities to look up a capacity. What's going to happen though is sometimes we're going to be looking up capacities that are like, what is the capacity if the length is 16.83 feet? There is no listing for 16.83 feet. But there is one for 16 and one for 17. And so what do? You break out that old linear interpolation. And you linearly interpolate between the quantities in the table to find the capacity. And so if you do that, you should get the same answer that you did before, minus a couple decimal points for rounding and for the fact that you're linearly interpolating. And so what we're going to do in class on Friday is we're going to go back to that problem that we just did, and we're going to do it again using method 2. And once we do that, then we'll look at design. I'm going to pull up the code again. That's all I got, everybody. I'll see you all